Something happened in the last 8 months that most people have not fully processed yet. 2 separate events, one in October 2025, one in March 2026, each one extraordinary on its own, together paint a picture of a technological moment that will define the next century of human civilization. Scientists are describing one of them as a genuine turning point. Government agencies are responding to the other with open alarm. Cybersecurity experts are using words like apocalypse and the world is not prepared. And at the center of all of it is the same force, artificial intelligence fused with quantum computing, producing results that nobody, not even the people who built these machines, fully anticipated. This is the real story of what just happened. No speculation, no science fiction, just verified, published, peer-reviewed reality. And it is stranger, more consequential, and more urgent than almost anything else happening in science right now. Let us start with October 22nd, 2025. Because that day, Google made an announcement that landed quietly in the mainstream press but sent shockwaves through the physics and computer science communities worldwide. Google's quantum AI laboratory, based in Goleta, California, announced that its quantum processor, a 65-qubit superconducting chip called Willow, had executed a complex physics simulation using a brand new algorithm called quantum echoes. And the results were not just impressive, they were jaw-dropping in a way that previous quantum claims had never quite been. The Willow chip completed the simulation in seconds. The world's most powerful classical supercomputer, running the best available classical algorithm, would have needed several days to match it. That is a 13,000 times performance advantage, 13,000 times faster. And unlike Google's previous quantum milestone in 2019, when its 54-qubit Sycamore processor solved a problem in 200 seconds that would have taken a conventional supercomputer an estimated 10,000 years, but produced results only 0.1% of which were verifiable. The Willow demonstration was different in a critical way. This was the first time a quantum computer had executed a verifiable algorithm with real-world scientific applications. Not a synthetic benchmark constructed to make quantum hardware look good. A genuine physics problem, producing results that could be independently checked and confirmed. The algorithm at the heart of it, quantum echoes, was designed by Google's team to exploit something fundamental about how quantum systems work. The technique works by sending a precisely crafted signal through a network of qubits, disturbing a single qubit, then reversing the system's evolution to detect the echo that bounces back. When that echo is amplified through constructive interference, quantum waves building upon each other in precise alignment, it reveals how disturbances propagate across the entire chip. It is, as one of the researchers described it, like listening to the structure of a quantum system by the shape of its echoes. And what it allowed for the first time was the simulation of molecular quantum dynamics at a precision and scale that classical computers simply cannot match. To test it in the real world, Google's team collaborated with researchers at UC Berkeley and simulated 2 molecules, one containing 15 atoms, another containing 28 atoms. Quantum computers are uniquely suited to simulating molecules because molecules are themselves quantum systems. The electrons inside them do not follow the neat, deterministic rules of classical physics. They exist in superpositions, they entangle, they interfere. Simulating them accurately requires tracking an exponentially growing number of quantum states, exactly the kind of problem that paralyzes classical computers, but that quantum hardware is architecturally built to handle. The Willow results not only matched outcomes from traditional nuclear magnetic resonance experiments, confirming their accuracy, but revealed new structural details about the molecules that NMR alone had never captured. New information, new science. From a 65-qubit chip performing a computation that no classical machine on Earth could replicate. The man who co-led the experiment was Michel H. Deverett, a Yale physicist who, in a fitting piece of historical symmetry, had just shared the 2025 Nobel Prize in Physics for the foundational research that made superconducting qubits possible in the first place. In the 1980s, Deverett and collaborators at UC Berkeley had first demonstrated that electrical circuits could exhibit quantum phenomena, superposition and tunneling, the same properties that govern subatomic particles. That work became the bedrock of everything that followed. Decades later, the scientist who proved that quantum computing was theoretically possible was now standing in the room watching it become a practical reality. He told the New York Times that future versions of this technology will perform calculations entirely beyond the reach of any classical machine. He described the Willow demonstration as reflecting decades of painstaking progress, and the Nobel Committee, in awarding the prize, was essentially saying the same thing. This is the foundation of something civilization-changing. The Willow chip achieves gate fidelities above 99.9% for single-qubit operations, meaning errors are rare enough that complex calculations can be completed reliably. It maintains coherence, the delicate quantum state that qubits must hold to remain useful, for several microseconds. That sounds brief, but it is long enough to execute the complex sequences required by the quantum echoes algorithm. Error rates this low and coherence times this long represent the result of years of engineering refinement. In Google's 2019 demonstration, only 0.1% of the data gathered was correct. With Willow, the system is operating at a fundamentally different level of reliability. IBM, watching this development, has not stood still. The company has publicly stated that it believes genuine quantum advantage, the point at which quantum computers are demonstrably more useful than classical computers for real-world tasks, not just benchmarks, will be achieved before the end of 2026. IBM's own researchers wrote that they had already arrived at a point where quantum computing is a useful scientific tool capable of performing computations that even the best exact classical algorithms cannot match. In June 2025, IBM partnered with Riken, Japan's largest comprehensive research institution, to use its IBM Quantum Heron processor alongside the Fugaku supercomputer, one of the fastest classical computers ever built, to simulate molecules at utility scale, beyond the capability of classical computers alone. IBM is targeting a 200 logical qubit system called Starling by 2029. Microsoft, in February 2025, introduced its Majorana 1 chip based on topological qubits, a fundamentally different approach to quantum hardware that promises natural resistance to errors through exotic quantum states, with a claimed path to 1 million qubits on a single chip. IonQ, using trapped ion technology rather than superconducting circuits, demonstrated a 12% speed advantage over classical supercomputers in a medical device simulation in March 2025. The quantum race is not a single company sprinting alone. It is the entire field accelerating simultaneously, driven by hundreds of billions of dollars in investment and the shared recognition that quantum computing is no longer a distant theoretical possibility. It is arriving. The question, and this is where the second event of this story enters, is whether the world is ready for what arrives with it. On March 30th, 2026, 2 research papers were published simultaneously and independently that changed the global conversation about quantum computing overnight. The first was a white paper published directly by Google's quantum AI team. The second was a preprint posted to Arxiv by Oratomic, a startup co-founded by researchers from Caltech and UC Berkeley, including Dolev Blivstein, who had previously worked at Google Quantum AI before departing in early 2026 to co-found the company. Both papers addressed the same subject. Both reached similar conclusions. And both relied, in part, on the same tool to get there: artificial intelligence. The subject was encryption, specifically elliptic curve cryptography, the mathematical foundation that protects an enormous share of the world's digital security infrastructure. The encryption protecting Bitcoin wallets, the encryption protecting Ethereum transactions, the encryption securing countless online banking systems, corporate networks, and government communications. The security of the modern digital world rests, in very large part, on the assumption that factoring the large numbers underpinning elliptic curve cryptography is computationally impossible within any practical time frame. Quantum computers threaten that assumption, because Shor's algorithm, a quantum algorithm first described theoretically in 1994, can factor those numbers exponentially faster than any classical method. The question has always been, how big a quantum computer do you need to run Shor's algorithm at the scale required to break real-world encryption? Previous estimates put the answer at over 10 million physical qubits. 10 million. That is a machine orders of magnitude larger than anything built today. At that scale, breaking encryption felt safely distant, decades away, a problem for future generations to solve. The NIST, the U.S. National Institute of Standards and Technology, had set a 2035 deadline for migrating critical systems to post-quantum cryptography, reflecting the consensus that the threat was real but not imminent. Google's March 2026 white paper shattered that timeline. Using an optimized implementation of Shor's algorithm, refined through algorithmic improvements that were accelerated, the team confirmed with the help of AI tools, Google's researchers calculated that breaking the CCPU 56K1 elliptic curve encryption used in Bitcoin could be accomplished by a quantum computer with approximately 500,000 physical qubits and around 90 million Toffoli gate operations. 500,000 qubits. That is a 20-fold reduction from previous estimates. The full technical details of the optimized algorithm are withheld in the published paper for security reasons, but the results were verified through a zero-knowledge proof, a mathematical technique that allows the correctness of a result to be confirmed without revealing the underlying method. The finding is real, the reduction is real, and the implications hit the cryptocurrency and cybersecurity worlds like a shockwave. Project 11, a crypto security organization, described it publicly as the quantum alarm and warned that unconfirmed Bitcoin transactions sitting in the mempool, the queue of transactions waiting to be confirmed, could become targets for interception before they clear. Bitcoin's average block time is 10 minutes. Google's analysis suggests a sufficiently powerful quantum computer could crack a Bitcoin private key in roughly 9 minutes. The margin between safe and compromised is that narrow. And then came the oratomic paper, which made the Google results look conservative. The oratomic team, working with researchers from Caltech, UC Berkeley, and Dolev Blovstein, who openly confirmed that AI was instrumental in developing their algorithm, stating there is no question that we used AI to accelerate this development, adapted the same class of quantum algorithms for a different hardware architecture, neutral atom quantum computers. And they found something that researchers described as shockingly low. On a neutral atom platform with reconfigurable qubits, breaking P256 elliptic curve cryptography, the standard protecting a vast range of internet security protocols beyond cryptocurrency, would require only 10,000 qubits. 10,000, not 10 million, not 500,000. 10,000 reconfigurable neutral atom qubits. Companies are building neutral atom systems right now. PsiQuantum, which became the world's most funded quantum startup in September 2025 after raising $1 billion in funding, is pursuing million-qubit photonic processors. The hardware required to implement the oratomic attack is not a distant dream. It is on the current development roadmap of multiple companies. Nature, one of the world's most prestigious scientific journals, covered both papers with a headline that read, "The world could be caught off guard by quantum hackers before the end of this decade," much sooner than expected. Time magazine, covering the same developments, quoted Blovstein directly, "People in the know will be like, oh, it is coming. The world is currently, in my view, not prepared." Multiple quantum computing experts who reviewed both papers for Time agreed that the results could significantly shorten the development time of a quantum computer that poses a genuine threat to encryption. A 2025 survey of quantum researchers found a 39% probability that a quantum computer capable of breaking encryption would exist within the next decade. That was before these papers were published. Google has responded to its own findings by accelerating its internal timeline for migrating to post-quantum cryptography, setting a 2029 target ahead of NIST's official 2030 guidelines. Cloudflare, which provides internet security services to millions of websites and organizations worldwide, has announced similar urgency. NIST itself finalized its first 3 post-quantum cryptographic standards in 2024 and is pushing hard for adoption. But the gap between finalizing a standard and actually migrating the world's digital infrastructure to use it is enormous. Banks, hospitals, government agencies, telecommunications companies, and power grids all rely on cryptographic systems built on assumptions that these papers are now calling into question. The migration is possible. The tools exist or are being built, but it requires coordinated urgent action across an industry that historically moves slowly. And here's the part that makes this moment unlike any previous warning about quantum threats to encryption. Every previous alarm was based on theoretical projections, on estimates made by researchers calculating when hardware might reach certain thresholds based on current growth trajectories. This alarm is different. This alarm is based on actual algorithmic work done with actual AI assistance that has demonstrably reduced the resource requirements for a quantum cryptographic attack. The goalposts moved. They moved suddenly. They moved because AI found a path through a mathematical problem that human researchers had not found. The people who did the work are saying openly and publicly that the world is not prepared. What we are watching across these 2 events taken together is something that has never happened before in the history of computing. A new form of intelligence, artificial intelligence, is actively accelerating the development of a new form of computation, quantum computing, that is itself approaching the threshold of breaking the mathematical locks that protect the entire digital economy. AI finding the shortcuts, quantum hardware approaching the scale to exploit them. The feedback loop is real, it is accelerating, and it is being driven not by any single rogue actor or any single government program, but by the open, competitive, globally distributed engine of scientific progress doing what it has always done, finding the next boundary and crossing it. The scientists working in this field are not alarmists. They are careful, rigorous, peer-reviewed researchers who are using words like unprepared and shock because those are the accurate words. The Nobel Prize winner who helped build the foundation for all of this is saying future versions will surpass classical machines entirely. The AI researcher who used AI to break encryption timelines is saying it is coming. The quantum hardware companies are announcing chips and platforms and funding rounds that track, almost precisely, toward the thresholds these papers identify as dangerous. None of this is science fiction. Every number in this story, every claim, every result comes from published research, peer-reviewed journals, verified demonstrations, and direct quotes from the researchers who did the work. The discovery is real. The implications are real. And the window for the world to respond, for governments, financial institutions, tech companies, and individuals to migrate to cryptographic systems that quantum computers cannot break, is now measurably, demonstrably, urgently shorter than it was 1 year ago. This is what it looks like when a technological civilization approaches a threshold it built for itself without quite realizing how close it was getting. The machines are ready, the algorithms are sharpening. The only question now is whether the defenses keep pace.